Hi guys, welcome back. Good to see you. Um, Today I'm going to be telling you about the loss function. If I can get this to work, wonderful. Let's see. Yeah. Um, so we've been talking about learning. Learning is about basically reducing errors. We've been talking about having multiple ways of having some algorithms that can help us learn. And I described for you the basics of linear regression, where you have some function y that you're estimating, which is a linear function of x, and we can find these weights that we want using the um, normal equation that looks like this. So this was one way to find the solution. Then we talked about steepest descent, which said that basically you want to change W so that it becomes something that depends on the gradient of your cost function. So if the cost function is the expected value of your squared errors, if this is my cost function, then what I want to do is move in the opposite direction as my gradient of this error. So the steepest descent said, well, the gradient of this error is going to look like this. It's going to look like this, where this is the error. So that was the gradient. And then we also learned about LMS, which we figured out that we can remove our errors using just a single step. And here's the algorithm that we had for that. It was similar to gradient descent, except that it had this term here, which was the square root of the magnitude of the input. And it's curious. You compare these two algorithms, and you might say, well, what's going on here? Why is it that in this case we're dividing by this term, where we're not doing it up there? What's the difference between this? And today I'm going to show you that what we're doing is that we're not just finding the first derivative, we're also finding the second derivative when we're doing elements, and that we're dividing by the magnitude that you see in that denominator. What we're doing is that we are solving the problem so that in a single step we minimize the error. So I'm going to show you how that comes about today. And so to demonstrate this to you is that suppose we have the simplest problem. So we have a single parameter W, and so it's a scalar, and there's some cost function here that looks like this. Here's J, and there's a place where, we have the optimum W, which minimizes our cost, but we're up here. So up here is where we are, and we want to get to W star where the optimum value is. And what I'm going to do is I'm going to use Taylor series expansion to show you something. So Taylor series expansion. So let's take our cost function J, and we suppose we evaluate it at W star. And if we were to do that using Taylor series expansion, I can say, well, let's evaluate J at W plus the derivative of J, let's call that J prime, dJ dW, evaluated at W, and that would be multiplied by W star minus W. So that's the first derivative of my cost multiplied by the distance from W star to where I am. And then, I have the higher derivatives, 1/2 the second derivative of J plus so forth. So that's a Taylor series expansion showing you how the function J at the place that I'm interested, W star, is related to where I am, W, plus the first derivative of that function, plus the second derivative of that function, and so forth. So now let me write the same thing for the first derivative of J. So the first derivative of J at W star. So at this point here, the first derivative, of course, is going to be 0. But what is that going to be written? I'm going to write it in terms of the first derivative at the location W. So that's equal to the first derivative at W plus the second derivative at W times W star minus W. And that's equal to 0 because I'm at the bottom of the hill at W star. So let me stop for a second. Let's see if you understood what I just did. So what I just did is that I wrote the Taylor series expansion for the function J at W star, this equation here. And then I did the same Taylor series expansion for the derivative of J prime at W star. So I can do it for the function J, I can do it for function J prime. Does that make sense so far? So it's a quadratic function in this case, so I don't have anything above the second derivative. Everything else is 0. Okay, so why is this useful? Why is it useful for me to do this? Well, the change that I want to make to my parameter W is this. This is the change that we should make. This is the change that I should make to W. So if that's the change that I should make to W, let's solve for this. So then this delta here, what is that? That is the first derivative, since I'll work it out so we don't have to skip any steps here. So the first derivative is going to be equal to the second derivative. So therefore, this term that I want to change is minus the inverse of the second derivative times the first derivative evaluated at W. Okay, so that's a nice little equation that we just found. I'm going to underline it for you. So that says the optimum change that you should make to completely remove the error is to look at the first derivative, the gradient that you have at the location where you are, and then scale it by the inverse of the second derivative. That's how you would completely remove the error if the cost function is a quadratic in the parameter space W that you want. Now, I just did this for W where it was a scalar. It was much more interesting, of course, if W is a vector. But before I continue, let me ask, do you have any questions about what I just did? All I did is use the Taylor series expansion to write the cost function at the optimum W. And with respect to where am I now? I'm at W. W star is where I want to go. Okay, what is the value of the function that I want to go at W? And the first derivative at that location, which happens to be the minimum of my hill, has to be 0. Therefore, I can make my assertion that delta is the optimum change that I should make in my weight is the inverse of the second derivative times the first derivative. All right. So what happens if W is a vector? So now that these derivatives are going to now become more complicated, but basically the story is the same. So let's write the Taylor series expansion for the case of if W is a vector. So the cost function J is still a scalar, but now W becomes a vector. So W star. So J is a scalar, W is a vector. So now I have, that's J at W plus, now I have the first derivative with respect to W. So this is going to be dJ dW, which is going to be a vector of size W. But I have to now multiply that by delta, which is W star minus W. And now in order for this to be a scalar, this has to be a transpose here. Did you understand it? Does that make sense, what I just did? So J is a scalar. The derivative of J with respect to W is a vector of size W. So that first derivative J prime with respect to W is a vector of size W, I have to multiply it by delta. Delta becomes a transpose. Now I get a scale. That's J. And I have the second derivative. 1/2. Now the second derivative of J with respect to W becomes a matrix of size W by W. So I take a derivative with respect to W, then I take the derivative of the rows with respect to W. I get now a matrix of size W by W. So now in order to get a scalar, I have a delta transpose here and a delta here. So instead of delta squared, I have a delta transpose in the front and delta in the back. Now I get a scalar. That's the Taylor series expansion of my cost J with respect to W star. So the first derivative, the same way we just did before, the first derivative of J with respect to W evaluated at W star. So now this is a vector, whereas this was a scalar. So I just found the derivative of my cost function with respect to W. W is a vector, therefore dj dW is a vector of size W. And in fact, so if W is W1, WD, so that's a D by 1 vector, this is a D by 1 vector as well. So the first derivative is a D by 1 vector. Okay, now I'm going to use the Taylor series expansion on this. So the first derivative of J with respect to W evaluated at W star, that's a D by 1 vector, that's equal to J evaluated at W plus, now I have the second derivative, J double prime evaluated at W. So the second derivative is going to be a D by D matrix. And what I want is a D by 1 vector. So this is getting multiplied by delta. This is a size of W, which is a D by 1. So then things work out. Now this is going to be equal to 0. The first derivative at W star, I'm at the bottom of the hill, is going to be 0. This 0 meaning it's a D by 1 vector of zeros, a whole row of zeros. So now I solve for delta. So now delta, so let's write this out. So I get J evaluated at W is equal to minus J double prime value at W times delta. So now delta is minus the second derivative inverse times the first derivative, where this term here is a D by D matrix. This term here is a D by 1 vector. Delta is a D by 1 vector because that's the number of weights that I have. And so W becomes W plus eta times delta. Okay, so that means that, W plus eta times, in this case, a minus eta times the second derivative times the first derivative. Okay, so this tells us that we can scale our learning rule so that what we're doing is not just finding the gradient, but also finding the second derivative of it. And that's going to tell us how much we should change, how much we should learn from error. And now I'm going to show you that if you go back to our learning rule here, this term here, this is the second derivative. So that's what that is. That's the relationship between this. So let me go back to now where we are here. But before I continue, let's see if you have any questions about the Taylor series expansion. Yeah.
So we know that after the third derivative, everything is 0. It's quadratic.
In this case, it's quadratic. After the second derivative, there's nothing beyond.
Yeah. And that's because we use like mean square.
Yeah. No, because the problem is linear in W. Right. So remember that your Y is a function of W. And that means because Y is a linear function of W, J is a quadratic function of W because you're squaring it. So squared error is by itself could be a nonlinear function of W, in which case you may use whatever number of derivatives you want. But if it's a quadratic function and you have a linear relationship, then J is a quadratic function of W, which means you can stop at the second derivative. Good question. Thank you. Okay. All right. So let's demonstrate now that when I had at the denominator the magnitude of x squared, that was the second derivative that we were dividing by. So let me show you this. So my cost function is the expected value of the sum of the expected value of my squared error. So this is my cost function. And in order for me to have a good learning rule, I wanted gradient, I want the first derivative, and I want the second derivative. So let's see what that tells us. So this J here is a scalar. And now I'm going to find the derivative of J with respect to W. So this becomes a vector of D by 1, where W is a D by 1 vector. So let's find the derivative of this. This becomes 2 over n. Let's find the derivative of the inside with respect to W. And then I have the minus W transpose X, the derivative of that with respect to W is this. So that's my first derivative. The second derivative, the way I write it is as follows. So as I mentioned to you, the second derivative is going to be a matrix. That's a D by D matrix. And what you're doing is that, so dj dw is a vector. Each row of this vector is some function of W, W1, W2, W3, W4, whatever. And now what you're going to do is that you're going to take that first element, and then you find the derivative with respect to W1, W2, W3, W4. That becomes the first row of your second derivative. Then you go to the second row and you find the derivative with respect to W1, W2, W3, W4. That becomes the second row of your second derivative. So you build up this. This is why it's written as dW, dW transpose. So you're finding first with respect to W, then with respect to W in this way. So it becomes a matrix of D by D size. So what is this? So we're going to find the derivative of this equation here with respect to W again. So that's going to be 2 over n. The sum, I is equal to 1 to n. And the only term that has W in it is the second term here. So that becomes W goes away, xi, and I'm going to put a transpose here. And I'm going to show you why that's required. So look at the size of x. So what is the size of x? X is a size D, is a D by 1. This becomes a 1 by D, and so x times x transpose is of the proper size, D by D. So that's the second derivative of my cost function. So now my learning rule becomes W plus eta times, here's my learning rule. So what I need to do is subtract from it the opposite of the gradient. And I think, let's see. Right. So let's see if I have. So my first derivative has this minus x in it. So let's put a minus there. So the second derivative is this 2 over n, is sum inverse. The first derivative has that minus sign, minus x, so I'm going to get rid of that, put a plus here. All right, so this 2 over n's go away. I'm going to put an eta in front of this, something less than 1, and I end up with okay. So you see how I'm taking x and I'm dividing it by xi, that x, the magnitude of x squared, and that's effectively what I was doing here with LMS, this term here. So that's where that comes from. This is called the Newton-Raphson method because we're using the first and the second derivatives. And in this case, eta is going to be always a number that's going to be between 0 and 1. I'm moving some fraction of my distance to the toward minimizing it. All right. So, okay, the next topic that I want to tell you about is what if we have variables that we're using to learn, but some errors are more important than us than other errors. So maybe certain errors mean more to us than other errors. Not all errors are the same. So we're going to have weighted errors here now. And the idea here is that we have some function of j of w, some cost function, and we're not going to have all errors be the same. And here's what I mean. I'm going to have some parameter p that's going to weigh my error differently depending on the data point that I get. So pi is going to make it so that, some xi might matter more than other xi. And for whatever reason that might be. And I'll give you an example of it. So what does this mean? So what I'm doing is that I'm introducing some matrix P here from the first data point to the last data point. And what I'm doing is I'm scaling my cost function so that it looks like this. I'm making it so that, some errors are going to cost more than other errors. And so if I were to multiply this out, here's what I have. And if I were to find the derivative of it with respect to w, so first of all, before I find the derivative, I can simplify this, as you recall, because j is just a scalar. This and this is the transpose of that. And because it's just a scalar, I can just find the transpose of them. So that becomes a minus 2 times w transpose x transpose py. And I find the derivative of j with respect to w, I get 1 over n. This is a d by 1 vector. Get x transpose So what I end up with is I set that equal to 0, and I solve for it. I get so now I have w is equal to an equation that provides me with a weighted measure of my errors in order to minimize the cost. Okay, so why is this useful? Why is it useful to have a weighted measure? Let me tell you about an experiment that one can do and use something like this. So let me give you an experiment in fMRI. So in fMRI, what you do is that you measure these images, and then you relate it to the task that's going on. So what we do is that you take n voxels in time. T is equal to 1 to t. So each voxel is an image, a component of this image, a pixel in your image. Because it's 3D, you call it voxel. And then you measure this voxel in time. So you have it at this time, 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 at this time. Each one of them is a time-dependent variable that you measure. Okay. Now, the idea is that what you're going to do is that you're going to relate that to behavior that's going on. Maybe they're moving their finger, maybe they're thinking about something, they're doing something. And each time an event is happening, so you say, move your finger, not move your finger, move your finger, not move your finger. You can think of that as a boxcar. Boxcar is going from 0 to 1, back to 0 to 1. And each event has its own boxcar. So maybe move your right thumb, move your left thumb, and so forth. And what you're going to do is you're going to build a regression model between what you measured and what the task was. And you're going to find this parameter beta that relates what you measured to what they were doing. Now, maybe what happens is that sometime during your measurement, the person moves their head. So during that period of time, your measurement is going to have errors in fitting that won't be the same as the times when they weren't measuring, weren't moving their head, meaning that your errors are going to be greater at some times than other times. And so what I'm going to show you is that we're going to use that idea that I just showed you, how to weigh your errors so you can fit your model. Okay, so you have n voxels. Each is a measure of a variable from time t to time 1 to time t. And so y is what you measure. That's the voxel, and it has a subscript little n in it, which is, it's one of these voxels among capital N voxels. And I have t by 1 vector to represent y of n. So this y of n is a measurement from this time to this time. How long is this? Capital T. So it's a t by 1 vector. This is equal to some matrix X, which is called my design matrix, times a variable that I'm trying to find, beta. Beta is like our W, and has a subscript n in it because it's associated with this voxel number, number n. So X here is a T by P matrix. And beta is a P by 1 vector. So what does this mean? So you have this data that you've measured in this voxel y, and you've done it yn, and you've done it from time point 1 to time point t. This is what you measure. You're going to set that equal to this design matrix. What is this design matrix? What that means is that they were doing something here, and then they did something else here, and then they went back here and did something else here, and so forth. And then they were doing, this is maybe move their right thumb. And then maybe there's a middle, maybe the pinky was moving here. Something like this. And so this is a boxcar that I'm drawing in time. Okay? And then maybe you have some other variable that was doing this. So forth. This is called your design matrix and is of size T, number of data points you took, times P, the number of parameters that you're trying to fit. So you're trying to figure out how these voxels that I measured are related to this, times this unknown, which is my beta, which is going to tell me this is a P by 1. How many variables that I have? Is it related to my thumb movement? Is it related to my pinky movement, and so forth? Right. That's how I'm trying to find the relationship between what I measured and the task that the subject was doing. Does this make sense so far? Okay. Yeah.
Question. When you move like a finger turns onto also end up putting another finger potentially, so wouldn't you end up with a matrix which might not be invertible?
So Yeah, absolutely. So for example, see in this position here, both of them are on. So in that case, they were moving both fingers. It doesn't have to be orthogonal. Okay. All right. So why did I introduce the idea of a weighted measure? The reason is because we can have sometime during this period of performance, maybe during this period here, this data was taken during a time when we noticed, oh, they're moving their head. So I still want to use my model. I don't want to throw away the data, but I want to weigh that data, those data points by the fact that my errors in fitting are going to be larger. Does that make sense? So what I do then is to say, let me describe a model that has noise in it, epsilon, sub n. This is the noise that I have in fitting my model. And I'm going to say the variance of epsilon is going to be something that's going to be time dependent. First data point, last data point, times sigma squared. It's going to be some matrix V times sigma squared n. And then when I fit my model, beta, what I'm going to do is that the solution to my model is going to be such that the greater the noise that I have, the less I want to worry about the errors in fitting my model. So the greater the noise in measurement, the less the errors matter. So if you look at the equations here, look at this equation. So that P now is represented with V minus 1. V is large when you have large noise, so you use the inverse of that to uh, weigh the errors in your model. Does that make sense? Yeah. Good. So maybe they're correlated, right? Yeah. So we wrote years ago, Jorn Diedrichsen, when he was in my lab, we worked on this problem and we wrote an algorithm that takes into account correlated, and so we have a paper on that if you want to look at it. All right. So the most interesting topic, I think, isn't how to minimize error, but to ask, what is the cost function when the brain learns? And so I've been using squared error, right? But that's just because finding derivatives of squares is easy. There's nothing, biological about it. At least I haven't shown you anything biological about it. So it's interesting to ask, if you wanted to find out when a person is performing something and they have errors, how would you know what is the loss function for them? How would you understand that? And the reason why I say this is because you've heard of people that are loss averse. A loss averse person is a person that is going to make decisions so that they're conservative, so that they're not going to win a lot, but they're not going to lose a lot either. Because for them, the cost of a loss is a lot higher than the gain of a win. And that's typical in most of us. So if I were to give you the opportunity to win $1, I say, all of a sudden I come and I give you $1, you feel good. But if all of a sudden I come and I take away $1 from you, you'd feel bad in a sense that is more than the goodness of feeling of winning $1. Losing $1 pains us more than gaining $1. We tend to be people that are averse to loss. Okay, so one can think about these questions mathematically and say, well, when people are performing some task, what is the loss function that they're using? And an interesting way to go after it, there are multiple ways to go after it. One of them is the people who study behavioral economics look at decision making, and they look to see, how likely is it that for you that you'd be willing to, risk something. And risk averse people are those who are particularly susceptible to loss, and therefore they don't put as much at stake. So it means that they won't win as much, but they also won't lose as much. But there's an elegant way to go after this problem mathematically using the formalism that we've been developing, and I want to tell you about that. So the paper that I want to describe for you is written by Conrad Kerding and Daniel Wolpert, and it's Proceedings of National Academy of Science in 2004. And I'm going to explain the experiment for you. I'm going to go through the math. I'm going to understand something about loss functions and how we can uncover loss functions using an experiment. Okay? All right. So there's nothing special about a quadratic loss function, except that it's mathematically something that is tractable. We could imagine other kinds of loss functions. So let me draw it for you. So you can have a scenario like this. So here's an error. So remember, loss is a function of error. So what kind of error can you have? Well, here's 0, here's 1, here's 2. So this is the errors that I'm going to have. And on the y-axis, so that x-axis is my errors. Y-axis is loss associated with that error. So I'm going to plot here loss of error. How much does it cost me if I have a certain error? So I can have a loss that looks like this. So this loss is 0 when my error is close to 0, but otherwise it's 1. So this kind of loss is something like if you were to go to a amusement park, and you've seen those kinds of games where there are these bottles out there, and you throw a coin, and if it goes inside the bottle, you win. If it doesn't go inside the bottle, you lose. So it doesn't matter how far away your coin lands, right? Either it goes in the bottle or it doesn't. They don't penalize you or to give you something more if it's close. So it doesn't matter if it's close. It has to go in. So that's this kind of loss. Does that make sense? Okay. Let's pick another kind of loss. I can also have a loss that's sort of linear, looks like this. So this is like the absolute value. So here, distance matters. If you're really close, it's good. If you're a little farther away, it's not as good, so forth. And so here, loss grows linearly. Now we've been talking about quadratic loss. Quadratic loss looks like this. This is squared loss. So here, you get penalized a lot for being far from the truth. So being close penalizes you a little. If you're far away from it, you get penalized a ton. So this makes it so that large errors are really bad. Linear loss, large errors are just a little bit worse than small errors. Does that make sense? And then you have the loss of associated with I don't know what to call it, the delta loss, the amusement park bottle loss. There, it doesn't matter how far away you are. So I can have different kinds of losses. So what we're going to talk about now is an experiment that tries to understand, well, what is the loss that most people, at least in this experiment, care about in a particular experiment. Can I find which loss is it that they're trying to minimize with their actions? And here's the way they did it. Well, before I go, does it make sense so far what we're trying to do? We're trying to find what's the function that people are using. What is the shape of it? All right. So what we're supposed to do is that when I have some parameter W that I'm trying to find, what I'm trying to do is find the expected value of the loss given W. So W is the parameter that I'm trying to find. And for whatever W you have some errors. That's going to cause some cost. That cost is called a loss. The expected value of that is what you're trying to optimize. You want to find the W that minimizes the expected value of loss. That's the problem of learning. Yeah, does that make sense? Okay, but you get to choose your loss function, and you could have it like I showed you, amusement park version, linear version, quadratic version, or some other kind of version. All right, so what do I mean by expected value of loss? Remember, what expected value means, expected value of anything is the probability of that anything. So if I'm looking at errors, then it's probability of the errors times that variable. So how likely is that loss? And then I want to do is that basically find the average value of that. So that's expected value of anything is the value of that thing times its probability. Integrated at the sum, and then, which is what that integral is. Okay, so here's the experiment that they did. What they did is that they had people hold a mouse in their hand. So I'm going to show you maybe a finger like this. So here's their finger. The finger is sitting on a mouse, and that mouse can move left to right. That's the only axis that we have. And this axis here is W. It's a parameter that they're trying to optimize. Okay, but on the screen, what they see is dots that are coming out of their fingers. I don't know if you ever played like Space Invaders, for example. This is a classic game from back when I was a kid. What's happening is that there are these missiles coming out of your finger, and what you have is a target. You have some target here. Let's call this. Let me draw it with a different line. Draw it like this. And there's a probability distribution associated with where these missiles are coming out of your finger. This is distribution of, let's not call it missiles, let's call it peas. Peas are coming out of this, you have a pea shooter. And peas are coming out, but there's a distribution associated with those peas. So there's a target. Target is that vertical line, but you have to move your finger in such a way that you maximize what? You place the finger so that on average, the peas land as close as possible to the target. That's the instruction. Place your finger in such a way that you get basically, on average, as close as we can to where the target is. Okay, now what we want to know is, how do people do this? How do they use, the amusement park type cost function? Do they use a linear one? Do they care about a quadratic one? And we're going to look at how we can solve this problem. How do we do such an experiment so we can understand their loss function? So let me begin by just giving you some intuition. So W is what we're trying to find. And to do that, let's imagine how we might solve this problem. So suppose that I move my finger slightly to the left. So my finger is in W1. Say this is W1. And over here is W2. A little bit to the left is W1, a little bit to the right is W2. So if I move my finger to W1, suppose that this is the function that describes the distribution of the p's. So this is probability of my errors given W1. If I choose my finger to the left, this is what it looks like. And suppose that this is 0. This is in error space, that's 0. Now, if I move my finger to the right, suppose I get a function that looks like this. And I'm drawing these functions asymmetrically, so you can see it has a long tail to the right. Let me draw it with a different color. Okay, so what am I doing? I'm saying that, look, when my finger's to the left, I get, a whole lot of things here, but then I get some of them that are way to the right. And if I move my finger to the right, I get some of the p's here, but then I also get a whole lot of p's to the right. Now, I have my target at some location. So what does it mean to try to find the W that minimizes this loss, the expected value of this loss? So suppose my loss is this amusement park. Is this. So only thing that matters to me is whether I get inside the target or not with this loss. Nothing else matters. I don't care how far they miss the target. I just want to maximize the number of P's that go inside the bottle. Suppose that's my loss. So how do I find the W that maximizes my gain, minimizes my loss? Well, the expected value, what I'm trying to do is find the W that minimizes the expected value of my loss. So expected value of my loss is the integral of the probability of that error times the cost it's going to have. Okay, let's do this graphically so I can show you what happens. So suppose I put my finger at this location W2. So I put my finger at W2. According to what I drew, I'm going to get a function of a bunch of errors that look like this. So this is 0. And I'm going to get some. This is going to be my errors. This is my probability of my errors given W. Okay, I have to multiply that by my loss. What is my loss? My loss looks like this. When I multiply, this is my loss. When I multiply my errors by my loss, what I get is a function that looks like this. When I integrate it, I am summing up these regions. So the red becomes the expected value of my loss. So I took the probability of the loss, the probability of having the errors, multiplied it by the cost of those loss, and I get that function. So if that's W2, if I have my finger at W2, okay, what if I have my finger in W1? My W1 cost is going to look like this. So now I have this thing that sits over here and it goes like this. So now if I multiply that by my loss function, what does my loss function look like? My loss function had this color. I get a function that looks like this. And if I were to integrate that, summing it up, they'll look like this. Okay, so which is a better way to go? Well, it turns out that if my objective is to minimize this particular loss function, then this is better. I ended up having less of, I didn't probably draw it well enough to show you this, but because I get more things inside the target zone, I have a loss that's less. So in this case, what happens is that you want to place, so if you have this loss, place W so that the mode, the peak value of the probability of your error given W falls at y tilde is equal to 0. So what this is saying is that if this is the loss that you have, then you want to place your finger in such a way that you get as many P's inside the bottle as possible, and you don't care about what's on the outside. So the experiment needs to do this systematically. And so what they do in this experiment is to say, let's write P of error given W so that it is a sum of two distributions. Where P1 is this, P2 is this. So when I sum them, maybe P2 looks like this. So when I sum them, the total becomes something like this, skewed, basically a skewed distribution. So when I do that, so if I now change A from a small number to large, where A is from 0 to 1. So when I do that, what happens is that the mode of my error function switches. The mode starts here when A is small, and then as I increase A, it's going to move over to the right. It's going to look like this. A large, A small. So as I change A, so the person is sitting there with their finger, and the P's are coming out of their fingers, and they're going to move it so that they find the location where most of the P's are going to go inside the bottle. But as I change this distribution, as A goes from small to large, then I'm going to move my finger so that I'm going to match the mode of my distribution so that I get most amount of P's there. So there's this parameter here they're going to change to see, do you track it? Do you move your finger to respond to the errors that you're making? If your distribution is this particular one, the delta function, then you will track the distribution that you see so that you move your finger so that most amount of P's go inside the bottle. And you don't care about having these large losses. You don't care that occasionally one of your P's is going to go way off to the side. As long as you get most of them inside the P's, inside the bottle. Okay, so that's if your loss function looks like this. But the experiment is clever. The experiment isn't just going to measure it for one error function. They're going to vary this error function, and they're going to see whether you track it with your finger so that you keep on getting most of the P's in there. Does that make sense? Okay, so we just did it for one of these error functions. Let's now do it for another one. Let's do it for a quadratic error function. Let's see what we get for that. So what should you do if actually it matters to you that some of these P's are way off? I get, maybe it bothers you that some of these things, of course, they're not going inside the bottle, but they're going considerably away from the bottle. So if that matters to you, then you're going to have a different solution to this problem. And let me show you what that solution looks like. So suppose your loss function is this. So you care about, sorry, let me write it like this. You care about those large errors. So now, if this is your loss function, how would you go about solving the same problem? What would be your behavior to would respond to this? So again, if your loss function is that delta, all you care about is the number of P's that go inside the bottle, then as the distribution gets skewed to the left or skewed to the right, you're going to track it so that most of these P's that are coming out of your finger go inside the bottle. Okay. Now I'm going to show you, we can set up the problem so that if your loss function is a quadratic function, you will not change your place of your finger. So we're going to set up the error function so that if what you care about is the quadratic cost, then you actually won't change your finger because you care about those things that are falling far from the bottle. All right. So let me show you how we can do that. So if the loss is a quadratic cost, then expected value of this quadratic term is what we're trying to minimize. And anytime you see a random variable that's raised to the power 2, you should be thinking about variance. Why? Because remember, variance of this variable, the error variable, is the expected value of the squared term minus the expected value of the quantity squared. So my task in a learning paradigm is to minimize this expected value because my loss function is squared error. But if I have a squared error, what I have is a term that's related to the variance and the mean being squared. So the expected value of the square of my errors is the variance plus the mean of my errors squared. Okay. All right. So the P's that are coming out of my finger are going to be placed based on a distribution that's made up of two normal distributions. So my errors are going to be defined by the sum of two normal distributions. One has mean mu1, variance sigma 1, and the other has mean mu2 and variance sigma 2. Oops. So I've described the problem to you. So I have my finger here, and each one of the P's that comes out of my finger is going to be dependent on this distribution that's sum of two Gaussians. One, mu1, sigma 1, the other, mu2, sigma 2. Okay, the sum of those two normals. Does that make sense so far? All right. So, okay, that's the probability of my errors. All right. So, what is the expected value of the errors given W, if that is my probability of errors? So let's walk through this and let's describe my mean and my variances. So look, what I'm going to do is that I'm going to show you that in order to minimize this, right? In order to minimize this, I need to find the variance of my errors and I need to find the mean of my errors and square. And so let's find the mean and the variance of my errors. Okay, so let's not worry about errors and W now. Let's just think about in theory, how would we do this? So you remember that expected value. So if my probability of X is 1 minus A times a normal mu1 sigma 1 squared plus A another normal mu 2 sigma 2 squared. So if x is some random variable, that's the sum of two Gaussians, then the expected value of x, the mean of x, is just 1 minus a times mu 1 plus a times mu 2. The variance of x, if I have sum of two Gaussians, the variance of x is the expected value of x squared minus the expected value of x quantity squared. So let's compute the expected value of x squared. So expected value of anything is the integral of that thing times its probability, which is 1 minus a times the normal mu 1 sigma 1 squared dx. And I have the second term plus integral of x squared times a times the normal mu 2 sigma 2 squared dx minus the expected value of x quantity squared, that's just this term here, 1 minus a mu 1 plus a mu 2 quantity squared. Okay, so let's look at this first term here. This term here. So this is some variable x that we've squared, and it has a mean mu 1 and variance sigma 1 squared. So we can write its mean as 1 minus a times x, its mean is mu 1 squared plus its variance squared. So x, its mean is mu 1. I've squared it. I want to find the expected value of x squared. Its expected value is going to be mu 1 squared plus sigma 1 squared. Its mean plus its variance. And the second term is going to be a times mu 2 squared plus sigma 2 squared minus this term here. Okay, so then the probability of my error given W is just 1 minus a times a normal. I'm going to call W at the mean of those P's that are coming. Let's call it W plus K1 sigma 1 squared. This is mu 1 plus a times a normal W plus K2 with variance sigma 2 squared. This is mu 2. So this is the distribution of these P's that are coming out of my finger. I'm going to parameterize it. So that distribution of those P's depends on my finger location, W. I'm going to add some constant to it, K1. I'm going to show you why. And that's going to just describe the P's that are coming out. So that's the probability of my errors. All right. I just showed you how do I find the variance of this. That's going to be 1 minus a times the mean. So this I'm using this quantity. I'm using this. I take this variables and I'm going to just write it in terms of the problem that I have. So mean mu 1 squared is W plus K1 squared plus sigma 1 squared plus A times this term minus so that's the variance of my errors. Now, the trick here is in this experiment, what you want to do is set K1 and K2. These are just parameters that you can set so that variance of this errors given W is equal to a constant, not a function of W. So if you could do that, then the expected value of your errors given W becomes 1 minus a W plus K1 plus A W plus K2, which is just equal to W plus K1 minus A K1 plus A K2. Then the expected value of my loss squared is the variance of my errors minus the mean squared, which is going to be equal to some constant minus W plus some other constant squared. So what this means is that I can set my distributions in such a way that W star, which is the arg min of the expected value of these errors. Look, I have this function here. Look, this function, the expected value of my errors, I just made it so that it just depends on W. And so the best thing that I can do is not move my W, not move my finger as you change the parameters of this task. As A changes, as you change A, which is you are moving the hills where these P's are coming from, you're moving it from left, you're moving it to right, but I made it so that if your loss function is a squared error, you should not respond. Because it's independent of the parameter A. So here's what the story was. Let me summarize it for you. So if you have a loss function that looks like this delta function, all you care about is getting P's inside the bottle, then you will respond to this distribution as I change the parameter A. As I move your errors from left to right, you will move your finger. But I can set up the problem so that if your loss function is squared error, you do care about those things at the edges, then you will be unresponsive to changes that I make in the parameter of your errors. You will ignore those changes if your loss function is a quadratic function. If all you're doing is minimizing the expected value of loss and your loss function is quadratic, I can set up your probability of error in such a way that as I change this probability of error, you will not respond to it. You would respond to it if your loss function is to maximize gain, which is to get the P's inside the bottle. So that's the basic idea of this experiment, which is change parameters in such a way that one kind of loss function will respond to it, whereas another kind of loss function will not. Okay, so at the end of the story, what you have is this parameter A, which is changing the probability of error given W, your finger location. And if your loss function is the delta function, you're going to get something like this. This is W as a function of A. If loss of error is equal to this. On the other hand, if your loss is a quadratic function, you won't change. You start right here. You stay right here. If loss of error is error squared. So you can dissociate these things. And then there are things in between. So maybe your loss is linear. It'd be something, I think it looks something like this. So you can actually then go and do the measurements. How do people respond? And the answer that they found was something like this. Something like raised to the power of 1.75. So something close to quadratic, but not quite. So people care about being way off, even though the task is get peas in the bottle. They do care about being far away from that. It's not just for them maximizing the um, the number of peas in the bottle. Okay, let me summarize this experiment for you. So our problem was, how do we know? How do we know what is the loss that people care about? And there's a way that one can go after it is by hypothesizing that, well, what you're trying to optimize is the expected value of this loss function. Find the W that minimizes the expectation average loss. Well, what is the loss? Is it a quadratic function? Is it a linear function, and so forth? And what they did is that they came up with a relationship between action W and errors, probability of y tilde given W, location of those p's with respect to the target. Then what they did is they said, okay, I'm going to parameterize these errors so that if what you care about is this loss function that's a delta function, you will respond to the distribution changes. If your loss function is quadratic, you will not respond. If your response is something in between, that tells me that your loss function is something in between. And from that, they concluded that the loss function was reasonably close to a quadratic function for this task. Yeah.
I guess it would somewhat matter what the task is. There's the way inverting finding you could have a really different loss function where kind of like an inverse Gaussian. You care up to a certain point about the actual magnitude, and then beyond that point, you give up.
Yeah, exactly. Yeah. And so the principle is that there's a way to compute your loss function. You give me the task, I'll try to figure out it, which is to manipulate the errors so that there's some parameter that changes the errors and see how people respond to their errors.
It's not a question, but doesn't it, for this to work properly, doesn't it suppose that the participant know the distribution?
Yeah, they have to have an unbiased sample of the distribution, right? So you have to give them enough time to observe the distribution.
Okay, so
Yeah.
when you finish the model, it's only after time.
Yeah. It has to be stationary, right? Yeah. And is that true? Do people have a sufficient time to see the distribution? Yeah. These are experimentally valid concerns. Yeah. And how much history do they have in their head? How far in the back? Because they can't see the distribution. They can only see now, right? But they have to keep a history to remember the distribution. Thank you, guys.